And here's how I say it, okay? L vector equals R cross P. All right, that's our normal, what we think about angular momentum. It's a particular type of vector, but I won't mention that right now. All right, intrinsic angular momentum is you're just born with. You just have it. There's no little m, there's no little v, there's no little r that you put together. Intrinsic means you grew up with it. All right? Just like you popped out with a charge, intrinsic means you popped out with an intrinsic angular momentum. Right? And so we call the intrinsic angular momentum of fermions spin. All right, it's angular momentum. What are the units of spin then? That's not a unit.
H bar.
H bar. Right, it's an angular momentum. Okay? So, what we find out then, what we're dealing with is intrinsic angular momentum. And so it's angular momentum, and so you start to get a feeling that it's another angular momentum. It has H bar. What is this formalism going to resemble? The formalism of intrinsic spin is going to resemble completely the formalism of
Angular momentum.
the angular momentum that we just did. Okay? So let's start to check this, all right? The first thing I'm going to say, and I'm not going to do it by proof, I'm just going to do it by stating, is the following. Is that Sx, Sy equals IH, H bar, Sz, Sy, Sz equals IH bar, Sx, and then Sz, Sx equals IH bar, Sy, and if you want, you can put all operators on these things. Because indeed, they are operators. All right, and so what does that say? What does that mean? That none of the individual components of spin angular momentum commute, right? So is there an eigenfunction out there that has the simultaneous values of Sx,
No.
Sy, and Z at the same time? No. All right? And it is true that S squared, Sx, or Sx, Y, or Z, doesn't matter. I mean this S squared Sx or S squared Sy or S squared Sz. I just didn't write it 3 times. Everybody see that? I was lazy. I probably should have done that.
Any one of the three.
Any one of the 3 does equal 0, commutes.
That's where you get your simultaneous eigen.
Okay, so does this all look familiar?
Does order matters?
Same thing with
Those
LML.
operators?
Does that look familiar?
Yes,
What's that?
exact same thing.
Yeah, these are operators, yeah.
Above though, does order matter in those?
Yeah, order matters, you'll get a minus sign. But when you switch the order, you'll still have that they don't commute, but you'll get a minus sign out
All right.
of it. Yeah.
So when you switch the order, it's just a minus sign difference over the result.
Yeah, not always. I mean, it depends on the case, but I think in this case you get minus. All right. So this looks familiar, right? What does this look familiar to?
Regular.
This looks just like angular momentum. All right. So these are the exact same properties of our regular angular momentum, and in our regular angular momentum, before we had an L squared on Y to the ML equals H bar squared L times L plus 1 times Y to the L ML. And then we had LZ on Y to the L ML equals ML H bar ML Y to the L ML. So what does that encourage you to find or to look for?
Eigenfunction for S
Okay, and what do you think that eigenfunction is going to look like?
Similar to the L squared function.
Okay, so how might I write it? How about this? S squared on something. Right? Now, here's the difference. Up here, when I see a spherical harmonic, I'm thinking of a function. Right? Something that has a function of theta and it's not a function of phi. Because I got that from the Schrodinger's wave equation, and it was definitely a function. All right? But now I'm dealing with spin. Right? And what do we know about spin? How many flavors does spin come in?
Two.
It comes in 2. All right? So the whole point that we looked at, when we looked at like Schrodinger's equation in the differential form, and we got functions, and those functions behaved like vectors, and they formed a Hilbert space, and when they formed a Hilbert space, we said they acted like vectors.
Yep.
All right? And so we could have said this. We could have said, you know, L squared on LML equals, and this is, you know, perfectly fine. L plus 1, L
H bar squared.
all right, and even h bar squared, and then LZ on LML, that equals h bar ML, LML. So if you want, this is like the Schrodinger representation from the wave equation with functions.
Yep.
And then what did we extend it to? To the matrix representation. And in particular, we made this abstract, complex abstract vector space.
Right.
All right? We just made these into vectors as it was easy.
Function, just abstract.
Exactly, instead of worrying about the function. All right, so now we have spin. Yeah?
Where does the unit of Planck's constant show up with spin? I thought, where did that show up? I thought it was just 1, 0.
It's an angular momentum, so it has to have units. And, you know,
So is it
it
one?
first shows up in Planck radiation.
So, but is it going to be like 1 Planck's constant of 0?
The real place this shows up is when you do a Stern-Gerlach experiment. And when you do a Stern-Gerlach experiment, it will depend upon what your magnetic dipole moment is, and your magnetic dipole moment depends upon spin. And when you do a Stern-Gerlach, it splits into 2.
Yeah.
And if you figure out how it splits into 2, you figure out that the 2 halves have an angular momentum of h bar over 2.
When people write 1, 0, they just drop the h bars, just to make it simple.
I agree completely. if
So
you
there
do
is
that.
an h bar, but it's just a drop.
So what we're going to do is when we make operators, we're going to throw in the h bar with the operator. All right? Okay. So how about this? How about if we do something like this? And now you'll see why I tagged the L on the ML. How about this? S, MS. So what is this? This is my spin, my abstract spin number. And this is the projection of my spin. Right? That's why I put the MS there. And what's that going to equal?
H bar.
IH.
Yeah, h bar squared S plus 1.
Cupcake, huh? And what about SZ? What is SZ operating on to pull out of this cat?
H bar MS.
H bar MS, S MS. And what does MS represent?
Projection of spin.
Projection of the spin. So let's draw our picture. What does spin look like? Here's X, Y, and Z. What do I know the Z component always is?
H and M.
It's H bar MS, right there. And therefore, where is S? S is some vector out like this. The magnitude of S equals H bar squared, H bar, the square root of S times S plus 1. And then again, kind of picture this as a vector that's rotating. As this vector rotates, you will always get the Z projection of H bar MS, but the projections of the spin in the XY plane is always going to be uncertain. And so that's the best picture we can get. So, you know, the other thing is this is kind of like a maximally informative states. You know, for L and for S, these are the maximally informative state. It has the most information we can know about these things. All right, we
Because it's
can't.
exactly H bar 02.
Yeah, well, the spin, we want not even get there. Just that it has a value and it has a projection in the Z, and I can measure those two exactly, but I can't tell you exactly what the projection in the XY plane is.
That kind of makes sense.
Okay, the distinction people often make is when we look at like a top that's spinning and rotating, then you can always know the angular momentum, the total angular momentum, and you can figure out the angular momentum in the x-plane and the y-plane and the z-plane. You can know those simultaneously. All right, but you can't know that in an electron, in a quantum system.
This is like you tie this into your MRI lecture for your pulse MRI stuff, right?
Yeah.
That's an awesome lecture.
Yeah, all right, cool. All right, thanks. All right, so that's what's going on here. All right, so that's spin in general. And now what we're going to do is we're going to look in particular at a spin half system. All right, this is spin in general. Because remember, spin, the intrinsic spin of a fermion, oh, I think I just said a fermion. Intrinsic angular momentum of fermion, no, this is wrong. This is fermions and bosons, because bosons have spin too. What's the intrinsic spin of bosons?
Integer.
Well, it's integer. Yeah,
It's
so,
whatever.
it's integer. So this formalism that I just developed here is for, you know, just spin in general. Okay? I can't believe I screwed up there. Can you edit that? Yeah.
I'm gonna put offspring in it, in that part when you stop the class. I'm just gonna clip that into the song.
All right, that'll work. All right. So now let's look in particular at fermions with an intrinsic spin of a half. Okay, let's give an example. Okay, so this is a good example. Excuse me.
Okay.
A fermion electron with spin a half. All right, so first, how do we know? How do we know? All right, one answer is Stern-Gerlach experiment. Okay, if you crunch the numbers, you know, this is an inhomogeneous magnetic field right here. Then you get a separation over here. The separation, now I'm going to be offspring again. The separation is proportional to mu, which is the magnetic dipole moment of the electron, which is proportional to the z projection of the spin. Let me do it this way. The distance of separation is proportional to the magnetic dipole, the z component of it, which is proportional to the spin in the z direction. And when you go through and crunch out those numbers, what you find out is you get Sz equals plus or minus h bar over 2. All right, and so I'm not going over that in great detail. We did it in modern. Griffiths actually covers it coming up. All right, I'm using it as a if we know about it to begin with. Okay, so our goal then is to create a complex abstract vector space for spin, and in particular spin half system. So let's create the complex abstract vector space for spin a half. Okay? Okay, first, what are the dimensions of the space?
2.
All we need is 2, right? It's either up or down. So 2. So can you guys think of a matrix, a ket, that's normal? I mean, that's normalized?
0, 1.
Okay, how about, yeah, so how about this? Up equals a 1, 0.